So, let us do a quick run through. It is intended to just sort of refresh your memory, and if there are any doubts or clarification, something in the notation, just ask, we can spend a few minutes. So, roughly lecture 12 was where we were introducing the noble identities, started looking at polyphase decomposition. That is more or less the start of the end of quiz 1 and the start of the portions after quiz 1. Then we talked about DFT filter banks and their properties, and then the 2-channel maximally decimated filter bank, the various solutions. Actually, we looked at 4 different solutions. So, the task for us now is to quickly review the items from lectures 12 onwards. So, lecture 12, the lecture numbers may be slightly shifted, but more or less this is the sequence in which we covered. Lecture number 12, we looked at the structure of a multiplexer and a demultiplexer, okay, and the form of the demultiplexer that is most convenient to us is the following form. Let me take the case of m equal to 3, downsample by a factor of 3, advance operator, downsample by a factor of 3. This is also downsample by a factor of 3. Okay. So, if you were to write down the, if this was x of n and x of 0 was going on the upper branch, then x of 1 will come on the lower branch, x of 2 will come on the second branch, then the next time instant it will be x of 3, x of 4, x of 5. This is what we also refer to as the blocking operation, creation of blocks. Notice that these are non-overlapping blocks. If you downsample by a number less than 3, then you will get overlapping blocks, and this is what we designated as a serial to parallel converter, serial to parallel converter, serial to parallel converter of dimension m, 1 in, m out, and this is a notation. So, if you see serial to parallel with m, it is the one with the delays. Of course, you can have a demultiplexer which works with delays, then the outputs are slightly shuffled, and again it is interesting to see what those what comes out if you replace the advance operators with a delay operator. And then on the other side, if you want to look at a multiplexer, operation which is most convenient for us, again I will take the case m equal to 3, 3 parallel streams connected or added with a delay operation. So, this is an added summing node, upsample by a factor of 3, a delay. Again, notice the arrows going upward, this is a summing node. So, this is the form of the multiplexer that is most convenient, and again if you fed in x of 0, x of 1, x of 2 as a block, what would come out would be x of 0, x of 1, x of 2, which is the logical sequence in which we would expect the data to be present, and the notation for this is m inputs. We refer to this as a parallel to serial converter of dimension m. So, again this is the standard definitions. Of course, you can mix them up a little bit and get slightly different outputs. Okay. So, if you were to look at the movement of the demultiplexer switch, then what you find is that if you have this structure with the advance operators, then it is going in the clockwise direction. Otherwise, you will find that it is going in the anti-clockwise direction. So, this is a useful form, because for example, if you wanted to compute the FFT with non-overlapping blocks, this is what you would do. You would do a serial to parallel conversion, downsample by n, so that would give you non-overlapping sets of blocks, and we have looked at that type of. Let's move on. A couple of other results from lecture 12. We said that the interchanging of multirate blocks, upsampling by a factor of L, downsampling by a factor of M, these are equivalent under certain conditions, okay, equivalent under certain conditions that L and M are prime. So, more importantly, more than the result is the ability to show these results mathematically. Okay, so let me just write one side of it. So, if this is x of n, let me call this as x1 of n, this as y1 of n, x1 of z would be x of z power L, because it is the upsampler, y1 of z is the downsampler, so it is 1 over m summation k equal to 0 to m minus 1, x1 of z power 1 over m w m raised to the power k. Okay, w is the DFT twiddle factor, e power minus j 2 pi over m, and this can be written as 1 over m summation k equal to 0 to m minus 1, substitute for x1 of z from the previous equation. So, this would be x of z power L over m w m k L, okay, and similarly we get an expression on the right hand side and make an argument that they are the same. All right. So, now if we then move on to the next important result, that would be the noble identities. If you have downsampling, a filtering block which is h of z power m followed by a downsampling by a factor of m, then you can interchange the two, provided we replace h of z power m with h of z, and similarly the upsampling also can be replaced, and the ones on the left hand side are the more efficient implementation. Along with this, we also looked at another important result, which we referred to as the time domain representation of the filtering in the context of multirate blocks. Time domain description. So, this is not an LTI system, because we have shown that the upsampler and the downsampler are time variant blocks. However, we are able to write the input and output in terms of something that looks like a convolution, and the interesting results are presented here. So, if I have the anti-aliasing filter h of z followed by a downsampler by a factor of m, okay. So, if this was x of n and this is y1 of n, we have shown that y1 of n can be written as summation k equal to minus infinity to infinity x of k h of mn minus k. Okay. So, make sure that you can get the same results. Second result, if we have x of n which is going through an upsampler by a factor of L followed by the interpolation filter h of z, y2 of n. In this case, we have shown that y2 of n is summation k equal to minus infinity to infinity x of k h of n minus k L. Okay. So, make sure that you got the correct relationship, and the third one, which is the combination of upsampling and downsampling, a fractional sampling rate conversion. So, if I have upsampling by a factor of L followed by filtering followed by downsampling, again the choice of the filter that is sitting in the middle depends on the values of L and M, whichever one is larger will determine the value, and in this case if this is x of n, y3 of n, y3 of n we showed is summation k equal to minus infinity to infinity x of k h of m n minus k l. Basically, it is a combination of 1 and 2. So, this is a way of representing the input output relationship, not strictly convolution, but in the form of a convolution type operation. Okay, move on to lecture number 13. I am sorry. Yeah, so again lecture number 13 may have started a little bit earlier, but probably the important result is the combination of polyphase decomposition and the filtering which is associated with the sampling rate change. So, anti-aliasing filter followed by the downsampler. We cannot take advantage of the noble identities except if you do polyphase decomposition. So, type 1 polyphase decomposition is says right h of z as summation k equal to 0 to m minus 1 z power minus k e k z power m. Okay. So, apply it and then use the noble identities. What we should get, the equivalent structure for this should be downsampling by a factor of m, delay downsample by a factor of m, dot a delay downsample by a factor of m. This would be E naught of z, E1 of z, again all the arrows are pointing to the right. This would be E m minus 1 of z, and all these outputs get added together. Okay. So, that would be the way you would take advantage for a, and likewise the same principle also applies if you wanted to do upsampling by a factor of L followed by the filtering to remove the images, then you would do a polyphase decomposition with L polyphase components. There is a type 2 polyphase decomposition which we have used not in the context of these sampling rate conversion, but we have used it in the context of filter banks. So, let me just introduce it here itself. So, h of z can also be written as summation k equal to 0 to m minus 1 z power minus m minus 1 minus k times r k of z power m. So, this is actually r m minus 1 of z power m plus z inverse of r m minus 2 z power m plus dot all the way to z power minus m minus 1 r naught of z power m. Okay. Now, if I were to just write down the type 1 polyphase decomposition, this would be E naught of z power m, z inverse E1 of z power m dot z power minus m minus 1 E m minus 1 of z power m. Okay. So, actually you can then map the equivalences between the polyphase components. I think somewhere between lecture 13 and 14, we also looked at the computational savings. If you do this, so let me, most probably it was part of lecture 14, we showed that the computational savings, if you do the polyphase part, is a factor of m than over the case where you did it in the direct form without any taking any advantage of the fact that you are downsampling. So computational savings, if I am doing for a factor of m, is approximately a factor of m. So huge advantages when you are sampling, making a sampling rate change of large magnitude. Okay. We also said that the application of the noble identity cannot produce unimplementable blocks. So noble identities have to be applied carefully. So for example, this is not permitted, Z inverse followed by a downsampling by a factor of 2, though mathematically is Z power downsampling by a factor of 2, Z power minus half. No, this is not allowed. So this is not allowed. Okay, and likewise we cannot do it for the upsampling also. So upsampling by a factor of 3 followed by Z inverse. If I did the noble identities brute force, then I would get Z power minus 1 by 3 upsampled by a factor of L, and this again is not permitted. Okay, because basically fractional delays are not realizable. Then we introduced the notion, or started to introduce the notion of filter banks, and there was an important result from decimation. Because these filter banks ideally would like to have maximal decimation. So when can you decimate a signal by a factor of m and not have any aliasing, basically no aliasing present? So we showed that if you had a spectrum, some complex spectrum, if this width is 2 pi over m or less, okay, less than or equal to 2 pi over m, then this signal can be downsampled without aliasing. So basically the downsample signal does not have any aliasing. Important result, because what will happen is you will get production of m minus 1 copies, they will be separated by 2 pi over m, and because of that the bandwidth is actually less than 2 pi over m, these images will not overlap with each other. Now this was a very important result which took us to the notion of filter banks, and the notion of filter banks starts from having a prototype filter and then producing other filters by shifting this one. So if this is H naught, then H1 is here, H2 is here, likewise, and if these had pi over m as their boundary, as their cutoff frequencies. So if this was minus pi over m to pi over m, the green filter would have pi over m to 3 pi over m. Notice that both of these will not cause any aliasing. Similarly, the blue filter also will not cause any aliasing when downsampled by a factor of m. Now, so this was a advantage, and there is a particular name for the filters that are filter banks where filters are derived in this fashion. They are basically called the DFT filter banks. The reason for the name is that these are all shifted by 2 pi over m, which is the same as a DFT twiddle factor. So H naught of Z is your basic filter or prototype filter, H1 of Z is H naught of ZWM, and H, let me use the same colors, blue is H2, H2 of Z is H naught of ZWM squared and so on. Okay, so you basically get m minus 1 filters. If you were to write it down in terms of the polyphase components, it is very attractive. H naught of Z type 1 polyphase components, k equal to 0 to m minus 1 Z power minus k e k Z power m, and then apply the DFT filter bank constraints, we get the following result, that the, where is my figure? Okay. So, this is what emerges from the, so if I were to apply the polyphase decomposition and apply the DFT filter bank property, then what I would get is a delay chain followed by the polyphase components followed by the transpose conjugate of the DFT matrix. I believe lecture 17 was where we were at this point. So, lecture 17 we also looked at the properties of the DFT matrix, belongs to the property belongs to the family of unitary matrices with suitable normalization. So, the notation is W. We usually talk about an n by n DFT matrix. So, the elements of this matrix are W subscript n I comma j. So, I is the row index, j is the column index. Okay. So, it would be e power minus j 2 pi over n times I times j, that would be your entry inside the matrices. And we have shown that through the properties of the roots of unity, that W dagger times W is equal to n times the identity matrix, which implies that W inverse is nothing but the W dagger divided by n, which is precisely the definition of the inverse DFT. Okay. We said that the recognition of the filter banks and the computation of FFT actually have a very strong linkage, and that linkage was established through the following analysis, where we said that the computation of a DFT requires you to do a serial to parallel conversion, step 1, followed by the DFT matrix, and then we computed the transfer functions between the input and each of the outputs. So, basically if you were to think of it as the as a spectral analysis, then the DFT coefficient x0 is the output of the of x of n passing through a filter whose response is given by this expression 1 plus yes 1 plus z plus z squared plus z power m minus 1. So, basically if you pull out the appropriate factor, you can show that this is nothing but the rectangular window, and likewise you can then show the transfer function between x of n and the second output to be a same filter shifted to the right by 2 pi over m, and this would be the x of m minus 1. So, this would be x of m minus 1. So, the last but one filter. So, we said that spectral analysis using the DFT can also be interpreted as a DFT filter bank, and maybe a few statements in this regard would be helpful. Again, I am sure you will remember it once you look at the expression. So, the DFT IDFT does not matter, we can both of them can be interpreted as filter bank operations can be interpreted as filter bank operation or spectral analysis using the following prototype filter, using H naught of z 1 plus z inverse z minus 2 z power n minus 1. Okay. So, again it is a rectangular, this is the prototype filter, and then all the other filters are DFT shifted versions of it. It is a very useful interpretation, because this also says that my spectral analysis using the DFT is not a very precise one, because the frequency response has got side lobes, and the height of the side lobes, if this was normalized to 0 dB, this would be at minus 13 dB, and it lead to some erroneous interpretations of the spectrum, and the first zero crossing happens at 2 pi over m. Okay. Now, if I wanted to get better spectral resolution, in the sense that I do not want spectral leakage, then we said the way to do it would be to introduce windowing. Okay. Introduce windowing, that would help us reduce the spectral leakage. The introduction of a window more or less would do something like this. It would make it a little wider, but would make the side lobes much less. How would this actually look like in the DFT structure? What would happen is you would introduce a multiplier here. What color would be a good one to use? So, basically call this as alpha 0, alpha 1, all the way to alpha, I have to erase something here. Okay. And last one would be alpha n minus, I am using m, sorry, m minus 1. Okay, so the windowing helps you with avoiding spectral leakage. Now, if you say that I want to have reduce spectral leakage and better spectral resolution, then the only way is to expand the size of the DFT, and one way to do that without increasing the DFT matrix size itself is to replace these coefficients with the So, that would be a way to do the spectral analysis. Again, we mentioned that this is an important observation. Now, in addition to this, there was one more result I believe which was highlighted. I would like to just use the same figure, maybe I will copy it and then rather than just keep overwriting it. Okay. So, let us work with this one now. We can also look at the scenario where the output has a downsampler by a factor m. Okay, this is, if this is m, take this as n. Okay. The role of the downsampler is to reduce the overlap between subsequent blocks. So, if you take n equal to 1, then what you get is just a sliding block where you have an overlap of m minus 1 samples between successive DFT computations. Okay. If you take n equal to m, then you get non-overlapping, strictly non-overlapping, and of course anything between n equal to 1 to m would be various degrees of overlap between the probably a popular one would be n equal to m by 2. Okay, so that will give you sort of 50% overlap, non-overlapping blocks. Okay, so again the same structure. The interpretation is that we are trying to do spectral analysis. We think of it either as a DFT or you can think of it as a DFT filter bank, where you have a prototype filter and then all of the other filters are part of the DFT filter bank, and you know how to improve the filter. You can think of it as a windowing, you can think of it as the polyphase components rather than as constants to be polynomials, and therefore get the advantage of the filters. Okay, let me move on quickly, because the next step was the interpolated FIR design, and the interpolated FIR design said that we could design filters taking advantage of the cascaded implementation. So, H of z can be implemented as g of z squared times I of z, and this would be the interpolation filter which removes the unwanted images that are present in g of z squared, interpolation filter. Okay. So, basically the underlying principle is multi-stage implementation, of the sampling rate conversion, implementation of either upsampling or downsampling. You can take advantage of this. Okay. A filter that is commonly used for as interpolation filter is the cascaded integrated comb filter, which is nothing but the rectangular window 1 plus z inverse plus z power minus m minus 1, 1 minus z power minus m divided by 1 minus z inverse. You can apply it for upsampling or downsampling. You can cascade many of these filters and then still take advantage of their computational efficiencies. Okay. So, that pretty much summarizes the parts on the multirate part. Now, moving quickly into the filter bank portion of it, the first step was to look at the trans-multiplexer. The trans-multiplexer has the synthesis filters in the beginning, followed by the analysis filters. We took the case where C of z is equal to 1, so therefore nothing is happening in the channel. What is happening is that upsampler produces copies of the spectrum, the synthesis filters are picking out the desired responses of the desired copy of the input signal. We showed the analogy to the OFDM transmitter. OFDM transmitter has an IDFT followed by an upsampler followed by a delay chain. The delay chain, the upsampler followed by delay chain is nothing but a serial to parallel to serial converter, and then we wanted to analyze what the IDFT actually was doing, and we showed that the IDFT is nothing but a filter bank which is exactly the prototype filter is the rectangular window. The second filter is basically you get a DFT filter bank from this. So, the idea of the OFDM transmitter is doing exactly the trans-multiplexer operation, with these F0, F1, Fm minus 1 being part of a DFT filter bank, where the underlying prototype filter is the rectangular window. Okay. So, then we move on to the special case of the 2-channel filter bank. The 2-channel filter bank, we have H0 and H1 as the analysis filters, downsampling by a factor of 2 then followed by upsampling by a factor of 2, then the synthesis filters. Very important that we are able to analyze it in detail and get the expressions. We represent output x hat of z in terms of a t of z times x of z, and another term which is a transfer function for x of minus z. Now, x of minus z is the aliasing copy or the aliased version of the input signal, and the goal would be to get rid of the any contribution of x of minus z. So, the alias cancellation constraints more or less universally consistent would be f naught of z equal to h1 of minus z. F naught should be a low pass filter, H1 is a high pass filter. So, if you take minus z is the shifted version which will become a low pass filter. So, it is intuitively that is a sanity check. Similarly, F1 of z is H naught of minus z with a minus sign. The minus sign is deliberately to get rid of cancellation. Okay. So, given this, we are guaranteed that the T of z can be written as, and along with the QMF constraint can be written as a H naught squared of z minus H1 squared of z. Okay, now the rest of the exercise was to see how to get rid of the magnitude and phase distortions in T of z. So, the first step was to look at a type 2 linear phase filter. Type 2 linear phase filter has got even order, no, odd order, yeah. So, even symmetry. Okay, so its n is odd as even symmetry, yes. If you then write down the expressions, we get T e of j omega is magnitude H naught e of j omega squared plus H naught e of j omega minus pi whole square, and we said that this could be implemented through the optimization of the stop band energy and a flatness constraint. So, that would give you complete elimination of phase distortion, but the magnitude distortion could have some minor ripples, depends on the order of the filter and how well you have done the optimization. The second option was to look at the polyphase decomposition and then show that T of z actually comes out to be z inverse E naught of z squared E1 of z squared, and if we could implement the filter H naught as a sum of two all pass functions, which we said was possible. We did not actually prove it, but we said that for a class of elliptic filters with appropriate constraints, we could do this factorization. The important thing is to know that it exists, then we could get rid of aliasing, get rid of magnitude distortion, but phase distortion would be present. Third method, where we actually did the all pass decomposition of the filter, we showed that under very specific constraints of symmetry and order, we could get the transfer function to be a naught, not a naught of z squared, it is a naught of z plus a1 of z, again into a1 of z. So, that again was a case where aliasing was cancelled, magnitude was removed, but phase distortion was present. Okay. Then we came to the fourth element, where we said that the QMF constraint we are going to apply it slightly differently, and for that we wanted to go back and look at some other results that were available to us, and that was the property of the mth band filter. Let me just quickly mention it so that we will have that result handy for us. The mth band filter, an mth band filter has the following property, that when you add the shifted versions of that filter. So, 1 over m summation k equal to 0 to m minus 1 h of z w m k. If this is equal to a constant, then we call h of z as a mth band filter, mth band filter. Okay. So, we showed that Nyquist filters satisfy this property. Nyquist filters which are used in our interpolation are actually the ones will satisfy the mth band property. Now, in addition to this, we also showed that if you had a a set of filters which are defined as power complementary, H naught of Z, H1 of Z, Hm minus 1 of Z as power complementary. This basically means that summation k equal to 0 to m minus 1 mod h k e of j omega magnitude squared is equal to constant or 1. Okay. Now, maybe I should have used a slightly different, let me call this as G. Then G of Z is the reason we show this side by side is if I have a mth band filter. So, by the way, this can be written as summation k equal to 0 to m minus 1 h k tilde of z h k of z equal to 1, right. That is the paraconjugate representation. Now, if we can represent or show that there is a mth band filter G of Z which can be factorized in the form of h of z times h of z. Okay. There is a specific name for this. This is called a spectral factor of h of G of Z, spectral factor of G of Z, because magnitude G e of j omega is equal to magnitude h e of j omega magnitude squared. So, basically it is like taking the square root of the magnitude response, but only under certain conditions you can take it. That basically means that your amplitude response must be strictly non-negative, and we showed how by lifting the amplitude response this is possible. Now, take this to the case where we want it to be just the half band filter. So, half band filter factorized into this form basically gives us a new way of designing the 2-channel filter bank, the aliasing cancellation constraint followed by an alternative way of implementing the quadrature symmetry. H1 of Z is the paraconjugate of H naught of minus Z. So, paraconjugate of with a minus sign. If we and we showed how to design this filter by designing a half band filter and then lifting the amplitude spectrum. If we do this, then we showed that the overall transfer function comes out to be z power minus n, or in other words we have achieved perfect reconstruction. So, this is the option that gives us perfect reconstruction. Of all the 4, this would be the one that would be the most attractive because it achieves this for us. Now, in the process when we talked about the all pass functions, we did derive the all pass lattice. I believe that was lecture 25. I will just write that down as the last point. We showed that there is a lattice structure where the order of the filter Gm at the with m lattice stages can be related to the transfer function with m minus 1 lattice stages in the following way: Gm minus 1 of z divided by 1 plus km times z inverse Gm minus 1 of z. And of course, there are very interesting properties that if Gm minus 1 is a causal stable all pass and mod Km is less than 1, then Gm minus 1 of Z will also be a causal stable all pass, and likewise it is an if and only if relationship. So, if you impose that constraint on Gm minus 1, then automatically this one also becomes the same. So, basically we showed that there are structures which will give us structurally stable all pass filters. Now, this was more in the context of showing that you can get all pass filters which will become sure to satisfy the factorization of the of a filter. But again, having studied perfect reconstruction, maybe these are limited in terms of their use in the filter bank context, but of course all pass filters have got several other applications for which this would be a very useful tool as well. So, the properties of an all pass, that is the last point I just want to mention. All pass, so this would be causal stable all pass. They belong to the class of functions which are termed as lossless. Input energy is equal to output energy if it passes through an all pass filter. There is a maximum modulus theorem. This is very important in proving the properties of the lattice. Maximum modulus property, we know that the all pass has got magnitude equal to 1 on the unit circle, h of z equal to 1 on the unit circle. The maximum modulus theorem derived from complex variable theory of analytic functions says that this is strictly less than 1 for mod z greater than 1 for mod z less than 1. Again, we have used this property without proof, but it is a standard result, the maximum modulus property of analytic functions. And of course, there is a third property which we did not explicitly use, but they exist for all pass functions, that if you have an all pass function, usually you write a transfer function in terms of magnitude and phase. Here the magnitude is equal to 1, so you can actually write it as e power j phi of omega, and if you differentiate d phi of omega by d omega, d phi of omega is a real valued function, can be differentiated. We can show that strictly less than 0, that means it is a strictly decreasing function, monotone decreasing function, if all poles are strictly inside the unit circle, okay, under this condition, inside mod z equal to 1. Okay, and I believe that was the span of what we have covered between quiz 1 and quiz 2. And most general form of an all pass filter, HAP of z is denominator polynomial z power minus n b tilde of z. This also says how will be the poles and zeros of a all pass function. Basically you will get the reciprocal conjugate as the, if you have a pole you will get a reciprocal conjugate as the 0, and because of, if you want to impose the condition of real coefficients, then you will get complex conjugate pairs, and of course the reciprocal conjugate pair will also be present. Okay. So this is just the material that we have covered in the class. Of course, if you have any doubts on assignment 4 or anything that we have covered in the lectures, please stop by between 5 and 6. TS and I will be there. Thank you.